Welcome back. So in this lesson, we are going to learn random forests. So as we said in the last lesson, a random forest is basically a slightly modified bagging algorithm. And it's one of the most used machine learning algorithms, right? So it's basically a collection of decorrelated decision trees, right? So that's why it's called random forest, right? So the forest is basically a collection of decision trees or a collection of trees, right? And why it's random? Because it's using the bootstrapping or the bagging idea, right? In the bagging idea, we did resampling with replacement, right? So resampling with replacement was actually done randomly, okay? So how we will build the random forest? In order to build the random forest, we will build a collection of decorrelated decision trees. So decision trees that are not correlated to each other. How? Basically, this is the pseudocode. For every tree, we are going to subsample the examples with replacement, right? So this is the bootstrapping step. So the first step is basically perform bootstrapping. And after that, for each subsample means for each bootstrap, we choose attributes at random, okay? So it's not only bootstrapping, it's also choosing attributes at random. So each decision tree will focus or will work on a subset of the dataset, right? It will not work on all the attributes. So let's say we have 15 attributes or 15 features. Let's say that for each tree, we will have 5 features or 6 features or 7 features, okay? And these features will be chosen at random. So we randomly pick features in each split. Why? Because if you remember, when we discussed the pros and the cons of the decision trees, we said that one of the most challenging problems in the decision trees, if one of the features contain so many values, right? Many values, then most probably it will contain most of the information gain, even though this feature might not be important at all. For example, we said the customer ID. Let's say we have a column called customer ID. So for each row, we will have a unique value, right? So we will have a number of unique values equal to the number of examples or the number of rows we have in the dataset. So we most probably are going to choose this feature, the customer ID, to split our decision tree, right? And it doesn't really contain any information, but because we are using the Gini index or the entropy, we did so, right? So by performing this step, by performing step number 2 in the random forest, we decrease the chance of this happening, right? Because we choose only subset of the dataset, and this also helps in decreasing the time for running the algorithm, because each tree will work on a subset of the data, right? So it will run much faster than the whole decision tree, okay? And for step number 3, we build the tree using only these random features and with the current subsample, okay? With the current bootstrapped sample. And for classification, when we want to perform a classification for a random forest or regression for a random forest, it's done by taking a majority voting of the classification yielded by each tree in the forest after it classifies an example. So very similar to what we have seen here, right? So let's say that the first classifier is saying it should be 1, and this is saying it should be 0, and this is saying it should be 1, and so on. So you will take the average or the majority voting, and the decision that we come up with is the final decision, right? So let's see how we can implement all this. And of course, we are going also to use the out of bag error for validation or for checking the accuracy of each subtree, right, in the random forest. So let's see how we can implement the random forest. So of course, we are going to use object-oriented programming because it makes more sense to use classes and objects instead of just functions, right? So we have a new class called, let's call it my random forest, right? To differentiate between this and the random forest, we have it in sklearn. And for the initialization function, we have, of course, the self to differentiate the objects from each others, and then number of estimators. So how many estimators we are going to use. Estimators are basically trees. So how many trees we are going to use. So by default, we will say that we are going to use 50 trees. Okay. And what is the maximum depth for each tree? By default, it's none. We can set it to be 3, 4, 5, whatever. And then maximum features. So maximum features is basically the percentage of the random features we are going to use. Okay. So if we say 0.7, so 0.7 of the features. Okay. And here we have also another attribute called bootstraps row indices. So this is basically which examples are in the current bootstrap. Okay. So as we know, this will be duplicated. So we might end up with one index appearing 5, 6, 10, 20 times. We don't really have any constraint on this because we are doing the resampling with replacement, right? And finally, we have an attribute for calculating the out of bag error. Okay. After that, we will have an empty list that contains the decision trees. Okay. And how we will construct these decision trees, we will loop over the number of estimators and we will append to this list the decision trees we are going to build, right? So we will call my decision tree. So this is our implementation. This is our class implementation for the decision tree algorithm, and we will call it with the maximum depth, right? So we will construct a decision tree, append it to the decision trees we have, and so on and so forth. Okay. And finally, we will set the attribute called decision trees in our random forest class to be the decision trees we build using the my decision tree class. Okay. So this is the initialization function for the random forest. After that, we will define a bootstrapping function. Okay. So as you can see, this bootstrapping function, the first letter in this function naming is underscore. Basically, this is a convention for naming the function. So as you can see here, we have underscore bootstrapping and here we have bootstrapping. So what is the difference? Basically, the functions that start with underscore are intended to be used internally. So they are not really intended to be used by the user. They are not intended to be called. Okay. So they are internal functions or private function. This is similar to private and other programming language. It does not really do anything. This doesn't really mean that you cannot call this function. Of course you can, but this is to let you know that this function isn't intended for you. If you want to call a function called bootstrapping, then most probably you will have a function called bootstrapping without the underscore. Okay. And we will see now why we need this function. So this function takes self, of course, and it takes the number of training. So this is how many training example in this bootstrap. Okay. And the number of features. So how many features in this bootstrap. And it should return the row indices corresponding to the row locations of the selected samples in the original dataset. Right. So it will return the row indices and it will return also the column indices. Okay. So what this function will do, very, very basic, randomly select a sample dataset of size number training with replacement from the original dataset. Okay. So how we are going to do this? Very, very intuitive. First, we will create the sample size. How? We have the number of trainings. So this can be 100, 1000, any number that you want, right? And then we will use the range function. Okay. So this will construct something like this. So let me show you here. So if I say range and let's say here 10, this will construct the function from 0 to 10. If we want to invoke this function, we will just write list. So as you can see here, we have a list from 0 to 9. Okay. So this will basically return the list we want. Okay. So this will contain the list. Okay. Let's go back here. This will have the list. Okay. And inside NumPy, we have a submodule called random. And inside the submodule called random, we have a function called choice. Okay, so what this function does is very, very simple. Let's take a look here. So let's take a look by just writing here. After that, let's say that this is z, for example, and here we will write z and 10. Okay, so as you can see, this will return a list. Okay, the size of this list is the same size of the input list, right? We have here 10 elements in z, right? So this will also return 10 elements. Okay, and as you can see, it will return these 10 elements or these 10 values from 0 to 9. So the same values you had in the original list, but with replacement. So as you can see, 5 was repeated 4 times, 4 was repeated 1 time, 6 was repeated 1 time, 7 was repeated 2 times, and so on. So if we run this again, you will see that we have a new list, right? So this will basically perform the resampling with replacement, right? So this is what this function is for. So this will return the row indices. And after that, we want also to return the column indices, right? So let's take this and copy paste it here to see what's happening. So here, as you can see, we have a function inside NumPy, inside the submodule called random, called permutation. Okay, so here, if we just write permutation, okay, and have here 10 and just call column index, you will see that this will return, okay, a list that contains 10 numbers also, okay, but as you can see, there is no repetition. Okay, we don't really have any repeated values. Okay, so this is basically what this function is doing. So if we give it 5, it will return a list of 5 elements or 5 values, and it will shuffle the values. Basically, it will shuffle the values. Now, after shuffling the values, what we want to do is that we want to come here, right after we have these 5 values, right? We want to take the maximum features. As we said, it's a percentage. So if we write 0.8, this will return. If we print this here, you will see it will print the first 4 elements. If we want to get the first 3 elements, then we can do this by changing this to be 0.6, right? So this will return the first 3 elements, right? So basically, we have the number of features multiplied by the percentage we want, and of course this can return a float, so we typecast it into an integer. So we take all the elements, all the values from 0 to the percentage that we specified here. Okay, so this is how we can get the rows indices and the columns indices. Okay, it's all using NumPy. We don't really need to implement it from scratch. Now, as you can see, this function just returns the row indices and the column indices. Now, we have another function called bootstrapping. And as you can see, this function has the same input as underscore bootstrapping. Okay, so let's take a look at this function. As you can see, initializing the bootstrap dataset for each tree. We didn't really fit the decision trees yet. We are just building the data for each tree. So we will loop over the number of estimators, okay, for I in range number of estimators. What we will do is that we will get a set of all the unique elements, right? If we have here the number of trainings, we saw this before just 2 minutes ago, right? We can have the range function, and after that we can use the list to construct a list of these values, okay? And after that we can typecast all this to a set. Why? Because if we want to get the difference between 2 lists, we cannot really do so, right? We saw this in a previous lesson, but let me show it to you again. So let's say we have x equal 0, 1, and 2, and then we have y equal 1, 2, 3. So if we want to subtract x from y, we mean here by subtract is that we want to get the difference. If we do so, you will see that unsupported operand type for list and list. So how we can do this? We can just come here and convert this to a set, and then come here and convert this to a set, and now we have 0 because 1 is repeated here and here, 2 is also here and here, and 3 is here but not here, and 0 is here but not here, right? So if we do it the other way around, if we come here and write set y minus set x, you will see that we have 3, right? So this basically means what are the elements in y that are not in x. And you'll see in just a moment why this is important. So we converted this list into a set, right? And we called it total, and this will contain all the unique indices for our dataset, so 0 till n, okay? After that, as you can see here, we are calling the bootstrapping function we created here. So as you can see, that's why we are using the underscore. We are using the underscore to specify that this function is only used in other functions, right? But it's not really useful for the user or useful by its own, okay? So here we have self.underscore bootstrapping. So we call this function with the number of training and number of features, and each time it will return row index and column index. And we saw a few seconds ago, if we call this function and then call it again, it will return different numbers, right? So it's random. So this will return different row indices and column indices for each decision tree. After that, we want to have total equal total minus set of row index, right? So the row index is actually a list, okay? So here we typecast it into a set and we subtract it from total, right? So why we are doing this? To get the out of bag error, right? Because these are the indices that we are going to use for training this specific decision tree. So the rest of the examples are not used in this tree, right? They are not used for training this tree. So we want to get what are these indices and put them in the out of bag error, right? Calculate the out of bag error using these indices. So that's why here we have total equal total minus set of row index. And basically after that, for the bootstraps row indices, we will append the row index, and for the feature indices, we will append the column indices, right? So this is what we are doing in this function, just calling the bootstrapping function and appending to the attributes we have for the random forest, okay? Now, till now we didn't really fit the tree yet. So fitting the tree is very, very simple. How we can do so? We will start by calling the bootstrapping function, right? So self.bootstrapping, number of trainings and number of features. So this will set the bootstraps row indices, the feature indices, the out of bag error for all the estimators, for all the decision trees. After that, we will loop over the trees, get the current bootstrap row indices, get the current feature indices, and get the current x. So current x can be a little bit tricky to understand. So this is the actual dataset, right? This is the complete dataset. So we will go to the indices we have for this bootstrap, okay? And we will take only these indices, okay? And we will take only these features, right? So we will take these features and we will take these row indices, okay? And the same for y, we will take the indices for the current bootstrap row indices, and the current decision tree is decision tree I, right? Because we built, as we said before, maybe 50 or less or more decision trees, okay? And finally, we can use the fit function, but not this fit function. The fit function inside the decision tree itself, right? Using the current x, the current y, and the initial depth is 0, okay? And we will fit this tree and iterate again, fit the second tree, and so on, okay? Now, how we calculate the out of bag score or out of bag error? First, we have accuracy as an empty list, and then we will loop over the full data set, right? The whole data set. And what we are going to do, we will loop over all the decision trees, all the estimators. Okay, so for t in range self number of estimators. And if I in self dot out of bag t, so the data that is not used in the current tree. Okay, so let's say that we have the first example, right? So I is 0. Okay, so we will go to the first tree and see for the out of bag for this tree, for the first tree, is the first index used for testing or it was actually used for training? If it was used for training, then this condition, we will not go to this condition. Okay, but if it was not used for training, then we will use the decision tree, right, the current decision tree, and try to predict x of I, because x of I was not actually used for training or fitting this specific decision tree. Okay, and we will use the feature indices for this specific tree also. Okay, and we will append this to the predictions. Okay, after that, if the length of the predictions is bigger than 0, then accuracy dot append nb.sum predictions equal y of I. So this will basically return, as we saw before, a list of true and false. So nb.sum will sum all the true values. Okay, and then we divide by the length of predictions, right? So this is the majority voting. Okay, by doing so, we will loop over all the rows in the dataset, see for each decision tree if this specific example was used for training or not. If it was not used for training, we will use the predict function inside the decision tree to try to predict this specific example. And then we will calculate the accuracy using a majority voting, and then we take the average of all the accuracies. Okay, so this is the total accuracy or the OOB score. So I know this was a very long lesson, but I think it was very important to understand bootstrapping and see how we can write code to do all this stuff. So in the next lesson, we will evaluate our implementation for the random forest and see how well it performs.